are kind of nice because what you're doing is you're ultimately working your way back to the original problem. And what we talked about on Friday, or Thursday rather, was that if you antiderive something that does not have a bound, meaning it doesn't have a limit, it doesn't have an upper and lower limit to plug in the numbers. So if we derive something with no numbers, so for example, it says find f if f prime of x equals x square roots of x. So that's kind of like saying, okay, the derivative is x square roots of x, so I want to work backwards and find the original. So the idea is that if I integrate the derivative, then I'll end up with the original. But because there are no bounds on this, it has to be the original plus c, because the derivative of any constant is 0. So there could have been a constant on this function, but when I antiderived it, it zeroed out and I didn't see it. So we want to find the antiderivative of x root x dx. So what we have to do is we have to simplify this algebraically so that x square root x is actually the integral of x. So this is kind of like 1/2 plus 1, so 3/2. Square root of x is 1/2. 1, so 1 plus 1/2 gives you 3.5. So the antiderivative of x to the 3.5, you add 1 and divide by it. So you get x to the 5 halves all over 5/2 plus that imaginary constant c. And this right here, this function is representative of f of x. So we can flip the denominator so that we get f of x equals 2/5 x to the 5/2 plus c. But we don't want to find, this is what we call a family of antiderivatives. It's a family because the c could be any number in the universe. What I want to do is I want to find the specific member of the family that has this as a true condition. So what I'm going to do is I'm going to plug 1 in for the x's and 2 in for f of x. So we say 2 equals 2/5, 1 to the 5/2 plus c. And what I can do is I can solve for c. So if I have a given condition, I can find the specific family member I want to find using my given. So 1 to the 5/2 is still 1. 1 times 2/5 is 2/5. So you get 2/5 plus c equals 2. So I'm going to subtract 2/5 away from both sides. So that c is equal to 1 and 3/5. Okay. Do we see how I found c? Sure. 1 and 3/5 is 8. Improper. I mean, you like improper. When I did my math in my head, it was easier for me to say, okay. To be honest, the AP exam is probably more likely to do improper than that. Okay. So here's where I said it was important to label correctly. So we are given f double prime of x. we have to integrate twice to get to f of x. So what that looks like is f of x is equal to the integral of the integral. So you can actually have two integral signs of f double prime of x dx. And this is ultimately leading us into the second fundamental theorem, because the second fundamental theorem is going to take place with deriving and antiderivatives. This right now, what we're doing, this is actually called the first part of the fundamental theorem. So let's find the antiderivative once. So if the original function, if what we're integrating is 12x plus 6x, does yours say 12x squared? Like mine's just missing one, right? It should be 12. Yeah. Dx. So let's find f prime. So f prime of x would equal 12x. So you add 1, so you get squared, divided by 2. Oh. Yes. So it's x cubed and divide by 3. So 12 divided by 3 is 4. So you get 4x cubed. 6x squared over 2. It is x squared, but you have to do 6 divided by 2, which is minus 4 plus c. So this is where it gets a little trickier. That's f prime. I have to antiderive f prime to get to f. So I need the antiderivative of all of this. So f of x, add 1, divide by the new one. So you get 4 over 4. You get x to the 4th. Add 1, divide by it. So you just get x cubed. Add 1, divide by it. So you get 4 divided by 2 minus 2x squared. A constant is kind of like the 4, right? This c is representative of a real number. When you antiderive negative 4, you put an x on it. When you antiderive c, you put an x on it. So this is like c sub 1 of x, and I still have an additional constant to add to it. So now I have two constants floating in my problem because I antiderived twice. So remember, this represents any real number in the world. So if it was 10, you'd have told me 10x. If it was negative 5, you'd have told me negative 5x. You have to treat it like a number. Now what we're going to do is apply my properties to find the values of c. That's why there are two of them. If I plug in f of 0, what happens to every single one with a variable? They all zero out, right? So that means c sub 2 must be 4. Because if I plug in f of 0, I get 0 plus 0 minus 2 times 0 plus c times 0 plus c sub 2. And this equals 4. So these are all gone. So that means c sub 2 equals 4. So now I'm going to use f of 1 equals 1. I'm going to say, okay, 1 equals 1 to the 4th, which is 1, plus 1 cubed, which is 1, minus 2 times 1, which is minus 2, plus c sub 1 times 1, plus, we said c sub 2 is 4, so we put in our 4. Well, what happens right here? 1 plus 1 minus 2 is, okay. So I'm left with 1 equals c sub 1 plus 4. So subtract 4. You get negative 3 equals c sub 1. It does not say find C1 and C2. It says find X. So you have to, for a final answer, say f of x equals x4 plus x3 minus 2x squared minus 3x plus 4. That is the fundamental theorem of calculus part 1. It says you can take any family of a function given knowns to find the original. That's what